One of the most intriguing results from this paper is how LLMs can effectively plan in complex, real-world scenarios, like guiding a household robot through a series of tasks to achieve a goal, such as fetching an item and placing it on a table. It's like watching a chess player think several moves ahead, but with AI handling everyday chores.
Exactly, and they accomplish this by using benchmarks that simulate these environments. Think of it as building a virtual playground where the LLM acts as the player. The paper categorizes these into areas like embodied agents, where the AI navigates physical spaces by modeling states and actions, sort of like mapping out a journey on a roadmap, where each state is a checkpoint and actions are the turns you take to get there.
Another fascinating result is how these benchmarks highlight LLM's ability to handle constraints, such as limited resources or unexpected changes, like replanning a trip when a flight gets delayed. This shows LLMs aren't just reacting, they're adapting strategies on the fly, much like a navigator rerouting around a storm.
Right, and the method behind this involves framing planning as a decision-making process, similar to a Markov decision process, or MDP for short. Imagine it as a choose-your-own-adventure story, where each page is a state, and your choices are actions that lead to the next page. The LLM learns to predict outcomes and pick the best path to reach the goal, balancing things like time and resources without getting bogged down in the math.
Building on that, the paper uncovers how planning promotes generality, meaning the strategies LLMs develop can be reused for similar problems, rather than starting from scratch each time. For instance, in games and puzzles, an LLM might solve a maze once and apply similar logic to navigate a website later. It's like having a toolkit of reusable blueprints for problem solving.
Absolutely, and they achieve this through world models, which are essentially the LLM's internal simulations of the environment. It's akin to an architect visualizing a building before construction. The model predicts what happens next based on current actions, helping the AI construct sequences of steps efficiently. This keeps things goal-oriented, focusing on outcomes without overwhelming the system with every possible detail.
What's really eye-opening is how the paper categorizes benchmarks into areas like web navigation or everyday task automation, revealing gaps where LLMs struggle with incomplete information or dynamic changes. This pushes the field forward by showing where AIs can plan like humans in structured tasks but might falter in unpredictable ones, such as adjusting to real-time traffic.
True, and the process relies on outcome reasoning, where the LLM evaluates potential results of actions within constraints. Picture it as a tightrope walker deciding each step based on wind and balance. The AI weighs options to maximize success, using policies that guide decisions like a well-rehearsed routine. This makes planning more robust and adaptable.
Finally, one more key insight is how these benchmarks recommend the best setups for different algorithms, guiding future developments in agentic AI. It's like having a menu of tests that help developers pick the right tools for tasks, from scheduling to puzzles, ensuring LLMs evolve to handle more complex, real-life planning.
To wrap it up, the paper's main takeaway is that Planet provides a solid foundation for evaluating LLM's planning capabilities, emphasizing state modeling, constraint handling, and reusable strategies. This could revolutionize how we build AI agents for everything from robotics to daily automation, making them more efficient and reliable in the long run. It's a game-changer for ML research, giving us clearer paths to smarter, more autonomous systems.